Okay, so welcome to the third and final installment of this energy series. So thanks for coming. We're going to look specifically at the sort of the formal scientific procedure for measuring change. Then we're going to look at calculating changes in energy. Then third, we're going to look at how to understand the sign. There's the sign of the change in energy actually has significance, and we want to better appreciate that. And then finally, we'll finish up by reviewing what endothermic and exothermic mean. Okay, so let's take a simple example. Let's take the growth of a child to illustrate how change is defined in a scientific measurement sense. So, as long as you take good care of kids and make sure they get plenty to eat, they usually grow, right? They usually increase in height. So first, in order to calculate the change in the height of the child, we need to know the child's height at the beginning of the period, the H initial, where the subscript I stands for initial and the H final, the F stands for the final height at the end of the time period. So to determine the change in the height, we just take the difference between these two values. However, in science, we typically calculate the change by subtracting the initial value from the final value. So H final minus H initial. This is worth thinking about for a moment because the sign of the change can be either positive or negative. Put simply, when the value of something gets bigger from the initial to the final state, the change in the value is positive. So when we're talking about children and their increasing height, that is something that is getting bigger. And so as we have defined the change in height here, the change you'll expect it to be positive. On the other hand, when the value of something gets smaller, the change will be negative. One other thing I just want to note real quick before we go to the next slide is I haven't said anything about this triangle here. I think you know what that means already, but the triangle in science, it can stand for several different things, but the triangle itself is a Greek letter. It's the Greek letter delta, okay? And pardon my writing here. I'm having a little trouble with my tablet. That's supposed to say delta. So the Greek letter delta in science usually means the change in some property. And so here we would say delta H. Hey, what's the delta H for this particular child? Where that value would simply be the final height minus the initial height. Okay? Now, let's see a couple of examples that illustrate the connection between change and the sign, just to make that feel a little bit more intuitive. All right, so first, let's imagine we have an object in a gravitational field where the force is directed downward. So clearly the potential energy increases as we go up. And we've assigned potential energies to these two levels. So when the object is raised from a potential energy of 25 joules to 75 joules, the delta is 75 joules. The delta is 75 joules, which is the final, minus the 25 joules, which is the initial. And that gives us a positive delta of 50 joules. Okay, now let's look at a second example involving temperature. If the temperature drops from, say, 100 degrees Celsius to 30 degrees Celsius, the delta T is 30 minus 100, or minus 70 degrees Celsius. Okay, so you should be feeling pretty good about how to calculate the change in pretty much any value. It's just the final minus the initial. Now we need to narrow our focus on changes that specifically involve energy. So when we calculate changes that occur with energy, the sign of the energy change has special significance. Let's go back to the simple example involving raising an object in a gravitational field. Experience tells you that this is going to require energy. After all, unless we believe in magic, we know the ball isn't going to rise up all on its own. The important point here is that when a change requires an input of energy, the change in energy will take on a positive sign. And this is obvious when you consider the fact that the final energy is greater than the initial energy. So the delta must be positive. So the bottom line, when a system must absorb energy to move to higher potential energy, this energy change is associated with a positive sign. And here, over here, I'm indicating that energy had to be absorbed by that object in order to gain 50 joules in energy. Conversely, when a system changes from a higher to a lower energy, such a change will release energy. Clearly, the object is losing potential energy in this example, but from the first law of thermodynamics, we know that the energy cannot just disappear. It is simply transferred elsewhere or is converted to a different form of energy. And again, the delta E calculation makes it obvious that the sign of the energy change is negative. You are subtracting a larger number from a smaller number. Now let's take a look at two terms, endothermic and exothermic. I'm sure you've learned about these two terms before, so I'm sure this will feel pretty familiar. But let's consider a couple of happy stick figure people, a man and a woman with nice fluffy blue hair. The man is running a temperature, and so we can assume that his temperature is higher than the woman's. Since they are holding hands and are in physical contact, the 0th law of thermodynamics tells us that heat will flow from the man's hand into the woman's hand. Okay, so I'd like you to pause the video for a second and consider this question. Is this an endothermic or an exothermic process? Go ahead, pause your video and come up with an answer. Okay, so if you were scratching your head a bit and wondering if you'd been given enough information, good job. The answer actually depends on whose perspective you're talking about. If you look at things from the stickman's point of view, the process is exothermic. So when we consider things from a particular perspective in thermodynamics, we are choosing a system. So in this example, if we want to look at things from the stickman's perspective, we're formally designating the stickman as the system. And so the process is exothermic because heat is flowing out. But what if we consider the situation from the stick woman's perspective? Oh, excuse me, just a couple of things just to help you remember what exo means and to associate that with things flowing out. Exo, it's like the word exit, as in exit the building, or exhale. When you're breathing out, your breath is coming out of your body. And both of those words start with EX. Okay, so on to the stick woman. If we designate the stick woman as the system, now the situation is reversed. Heat is flowing into the system, and therefore this is an endothermic process. And again, one way of remembering endo means in is like in the medical field. If you have to have an endoscopy, the endoscope goes into the body. But let's not think about that too much. I'd like us to try and put everything together now. But let's stick with Mr. and Mrs. Stick Figure for a moment. If we maintain that the system is the stick woman, let's go a step further and ask what would the sign be for the change in energy. I think you'll agree that when something is absorbing heat, as Miss Stick Figure is, their internal energy is increasing. Does that make sense? If you're cold and you stand in front of the fireplace, you will absorb radiant heat from the fire and increase the thermal energy inside your body. This increase in energy could initially be tracked by simply monitoring the temperature of your skin. The bottom line is that the final energy of the stick woman will be greater than her initial energy, and this leads to a positive delta E. Placing the system on the stickman would reverse the situation. Because heat is flowing out of his body, his internal energy is decreasing, and therefore the final energy of the stickman will be less than the initial energy, and this leads to a negative delta E. One final thought, if this relationship between the signs of the delta E's and the direction of heat flow still feels a little murky, then try thinking about this in terms of money. In this scenario, the amount of energy contained in a system is analogous to your bank account balance. That is, how much money you have in the account. When you take money out, like energy being released, you have to subtract the amount of your withdrawal from the balance. So money flowing out, or exo, of your account is associated with a negative sign, right? But when you deposit money into your account, like energy being absorbed, you add the amount to your balance. So money flowing into, or endo, your account is associated with a positive sign. So see, it's not too bad. Okay, so one final exercise. I thought we could create a little table here, and I would encourage you to do this in your notes when you're watching the video. So I would recommend, I'll pause here for a second, but I'd recommend making a 5-column table with 3 rows. The first row is the column headers, and we'll kind of fill this in, and this will kind of knit everything together that we've talked about. Okay, so go ahead and pause the video if you like, and set up your table. Okay, so here we go. Hopefully I'll be able to write without looking like too much of a kindergartner. So this all starts off with just a very simple picture. So the circle, this white circle, represents a system, any system, and the red arrow is the direction of heat flow. So clearly, in this situation, the process would be endothermic. So I'll just write endo for endothermic. In this scenario, the description of what's going on is heat is being absorbed. Okay, so I would write heat is being absorbed. I apologize for the writing here. There's a tremendous lag time going on with my computer, so it's very hard to write. Now, what would the change in energy be? Would it be a positive sign or a negative sign? Well, again, if you think about this in terms of a bank account, heat is like money flowing, and if it's flowing into the system, that's like a deposit, and so that's going to make a positive impact on your bank account. And likewise, the change in energy would be considered positive. If you were monitoring the system with some sort of a temperature tracking device, like a thermometer, you would expect the temperature change to be positive. That is, you'd expect the temperature to go up. Now, let's consider the reverse direction. So let's say we have a system where heat is flowing out. Okay, heat's flowing out. Alright, I think I better quit while I'm ahead there. Okay, so that's supposed to be an arrow going out of the system. So this would clearly be exo, right? Heat is exiting the system. And in this case, heat is being released. Okay, so heat is flowing, or is being released into the surroundings, and this would decrease the internal energy of the system. And if we were, again, monitoring the temperature of the system, that would be a negative change in temperature. The temperature would be going down. Okay, so thank you very much for your time. I hope this was helpful, and I'll see you soon.